Me mihi ka tika ki ngā mana whenua, ka mihi ki tātou katoa e hui hui mai nei, tēnā tātou. No mai, haere mai ki Stardome Observatory and Planetarium. A warm welcome to you all. It's so wonderful to have you join us here, albeit under slightly different circumstances than we had originally planned. Ko Victoria Travers Aho. I'm the Chief Executive or Pou Whakahare of Stardome Observatory and Planetarium, and it is absolutely, I'm just so pleased to be able to welcome everyone here tonight. And I've got a bit of a confession to start with, which is really that I'm neither an astronomer nor am I an engineer. So I feel like a little bit of a fraud being here tonight. But the great thing is that I'm supported by three of our volunteers who are some of their depth of knowledge, and particularly around the Zeiss, is just, you're in for a real treat to be able to hear the mātauranga and the knowledge and the experience that these three hold. I've been in the role at Stardome for about the last 6 months, and one of the things that really drew me to applying for the role, I have to say, was the memories of the first time I came to, well, at that stage it was the Auckland Observatory, when I was in my late teens, and I still remember walking up the stairs and into the dome to see the Zeiss. And that is still such a palpable experience for so many of our visitors. Some of you may well have had that experience yourself, and it could be while you're tuned in. It's such a, I'll talk about the romance of it, probably that's the best place I'm positioned to, but it is a very, very romantic space, and to be able to have access to a telescope on this scale, and just to be in the room with it and to be able to look through and share that human experience of staring up at the heavens and celestial bodies and planetary bodies. So it kind of brings it back to how the Zeiss ended up here, first installed and opened in 1967, and really, and Grant is going to talk a little bit more about this, but really Edith Winstone Blackwell's wish for Auckland is that exactly that people had access to a significant telescope. And so we're really, really so thrilled that through the work of our volunteers, the work of the Astronomical Society, we've been able to extend that access even further. And my three colleagues here are going to talk a lot more about how they were able to do that, and just so that we can still provide particularly young people with that opportunity to have their first telescope experience. So without further ado, I'm going to hand over and introduce you now to, we have three of our volunteers here, and they're more than that. They're kind of our kaumātua when it comes to this particular piece of machinery and the Zeiss. So joining me, and I'm going to hand over to them very shortly, is Grant Christie, Tony Messenger, and Steve Hennerly. Enjoy the evening. It's kind of going to be a bit of a panel discussion style. The team really are so welcoming of any questions you have. So please, and if you just use the chat function, or that the questions, just pop them in the YouTube feed that you're all looking at, and we'll also there'll be plenty of time at the end to answer any questions. Over to the team.
Right. Well, thank you very much, Grant Christie, and I'm going to just give a bit of a backstory to the observatory and the telescope. The picture you have on the screen at the present time is the observatory as it appears today, but it's grown a lot over its life. So we owe this really to Edith Winstone Blackwell and her husband Harry, but Edith left a bequest to the Astronomical Society of £7,500 in 1956, shortly before she died. She'd been a lifelong interest in astronomy, loved astronomy, always was telling her family about the stars, And and she wanted to make a sort of a lasting legacy, and I'm happy to say that it's worked out wonderfully. So the society had the job then of deciding, and it was sort of a fairly basic operation in those days, in the early 1960s, to determine which telescope they should buy with this quite a large sum of money. And they sought quotes from a bunch of the different manufacturers around the world, American and European, and finally settled on the half-metre Zeiss Cassegrain that you can see in the picture on the left. It was, we know that this Zeiss ended up making about 20 or 25 of these telescopes around the world, and we have one. It's a reflecting telescope with a half-metre parabolic mirror, which you can see a sort of a ray diagram of it on the right-hand side. So as the light comes down, hits the parabolic mirror, reflects up to the secondary mirror, which is about 20 centimetres across, and that reflects the light back down through a hole in the primary mirror to a place where you put a camera or an eyepiece and you look through it. And this Cassegrain design dates from about 1672 or 73 by a Frenchman who basically figured it out about the same time as Newton was working on his stuff. So this is the telescope as shown in waiting for shipment, basically, or packing up and shipping in the Zeiss factory. You'll notice that the mount has got a kink in it as it goes up. It's got a big pedestal foot, which in our dome is below the floor, so you don't see the pedestal foot. Then there's a pier that goes up, and then it takes a little sharp bend to the left, and that angle of that bend is our latitude. So when that mount is lined up correctly, then that axis points directly at the South Pole in the sky, which is exactly parallel with the Earth's rotational axis, so that the telescope can then track astronomical objects or stars and planets across the sky by simply a motor driving the telescope slowly at exactly the right rate, sidereal rate, and it keeps the star sort of very steady in the centre of the field of the telescope. So the drive worked very well. It was an electromechanical system, and it was sort of state of the art pretty much at that time. So the telescope, sort of like Carl Zeiss made them, for focal ratios it's f13.3, which is actually a very short focal ratio for a normal Cassegrain reflector. Most of them are about f16 or so. The total focal length is 6.650 metres. It's also got a finder telescope, auxiliary telescope on the side, which is a 115 millimetre diameter achromatic refracting telescope. It gives a lovely wide angle views, about 2-degree field of view. And it's also got a guide telescope, which we've now removed off the telescope actually. But that was there for guiding photography, but since we never used the telescope for photography, that telescope virtually never got used and it's stored away. And the dome that the telescope resides in was also supplied by Zeiss, and if you go around the world to different observatories that have Zeiss telescopes, you'll see that it looks strangely familiar. They've all got domes that look like ours. And it's a 5-metre diameter, and it's clad in copper, and looks pretty spectacular. And it also the telescope also came with accessories, most of which we had no real use for, but they were a good idea in 1960. I've already mentioned about the sort of broadly the shape of the mount and the fact that it's sort of the clock drive did a great job of tracking objects. We could track for 30 minutes with that drive without the stars elongating in any way. So these are just some archival pictures showing the building of the observatory, and this was in late 1966. I was at school at Mount Grammar at that time, and would pedal over from after school to see the progress as this was being done. And that just shows the dome being lifted on. The dome was assembled by Winstone workmen. It would have cost a lot of money for Zeiss to send people down to do anything here, so we were able to avoid that. And Winstone craftsmen actually did all the assembly of the dome. And this image, this is the opening day in 21st of March 1967. It was opened officially by Brigadier Sir Bernard Ferguson, and those are just of the notaries who were present at the time. I wasn't invited, I was just a newbie in those days. And so this was at about the time that the observatory opened. This is pretty much what it looked like. That's a Pat Hanley mural, was the main sliding door that was present on the front of the building and looked pretty neat. It accidentally got destroyed, unfortunately, about mid-1990s. But on the right-hand side, there was a lecture hall provided by the Auckland Savings Bank, and the rest was just blockwork and offices on the other side. And on the left-hand side of the dome there's an enclosed courtyard for viewing of the night sky with groups of people with small telescopes. And so this is sort of a view that it would look like operational, a lovely clear Auckland night, and just shows the telescope open and working. The dome has worked extremely well over the years. We've never had any trouble with that, and so has the telescope. The telescope got used not only for public viewing, which we had huge numbers of people turn up, and in fact over its whole lifetime, so probably well over 1 million people will have looked through the telescope on public nights. But it also got used for science, and this shows one of our members using an instrument called a photoelectric photometer, which is used to make very precise measurements of star brightnesses. And so a lot of the work of the observatory, the scientific work was measuring the brightness or the change of brightness of stars as they go through their lives. And it's work we still do today with newer instruments. And then in the mid-1990s, or in the early 1990s, should we say, it was decided the observatory either had to grow or die. Fortunately, the trustees were able to pull together a funding package of about $3 million, most of it in the form of a loan from Auckland City. And this funded the expansion of the observatory. Its floor went up fourfold, added a planetarium, and added a second dome, you can see there at the back, that now houses a research telescope. So it became a major public facility for Auckland. And then the telescope was getting pretty tired and just from use and wear and tear by about the mid-1990s. And we decided in the late 90s it was time to strip it down and restore it. Again, that work was funded, or the cost of it was funded by the Edith Winstone Blackwell funding that we had. So the telescope was dismantled pretty much completely, and all the paintwork was redone, all the metal work was done, the nickel plating was done, and the telescope came back to looking more or less like I remembered it when I was young, which was really great to see. And all the dome interior got renovated at the same time. And so looking from the back side of the observatory today, we've got the smaller research dome there with the original Zeiss dome, and the research dome now houses a separate telescope which is used for research projects. And it's the telescope is a smaller telescope. It's about a 0.4 metre telescope. It's a little bit smaller than the Zeiss, but it's mounted on a computer-controlled mount. And I won't get into the details of that, but essentially it means that the mount is computer controlled, and today we operate that telescope remotely through the internet, and it's can be told to move to places. You can open and shut the dome remotely. But the main advantage that we were missing on the Zeiss, this telescope, you could tell it to go to any astronomical object, and within about 20 seconds, the telescope would be pointing exactly at that object. So there was no time delay in going from one object to another, or very little. Unlike the Zeiss, which was at this time was still manually operated, you had to unclamp it and push a 500 kilo telescope, albeit well balanced one, and then try to locate the object in the night sky. And that was very slow. And so on public nights, you had a lot of issues with not being able to find objects. If you had scattered cloud, it was hard to find your landmarks in the sky, and it was generally a bit disappointing. Today, with the upgrade, we anticipated we would not have that problem anymore. So that's what this telescope provided us with the experience that told us what to do with the Zeiss telescope.
I had a question from one of our viewers, Ivan, asking what the purpose is of the copper cladding on the outside of the dome.
Waterproofing, basically. I mean, and it's a trademark that Zeiss followed. Generally speaking, most astronomical domes are painted white on the outside to reflect heat, to reflect the sun, particularly in places where the sun's intense. But it provides an elegant appearance, so it's really just keeping the water out. So this is just a sort of image that you can get with, well, this was taken with the research telescope of a sort of a nice galaxy. If you're looking through the Zeiss telescope with your eye, then you would, this would just be a faint little smudge in the sky. You'd see there was something fuzzy there, but you wouldn't see anything like what its structure was. So this is the power of a CCD camera, which is what we use on the research telescope, and we also have one now for the Zeiss telescope, so we'll be able to use the Zeiss also to produce images like this. And that's a Centaurus A, an active galaxy, and very popular photographic target for amateur photographers, and this is one of the sort of biggest globular clusters in the sky, so sort of like 500,000 stars in that blob.
Hi, I'm Steve. As Grant was saying, the research telescope out at Stardome is one of a number of telescopes that are used for research actively by amateurs in the Auckland area. Auckland Astronomical Society actually has another observatory out in Kumiu, where the light pollution is a little bit less. I know there's a question in the chat there about has light pollution got worse over the years. The answer to that is yes, but LEDs seem to be helping somewhat, as long as we're careful with LEDs for that one. Interestingly, out at Kumiu, the mount that Grant was describing, that the research scope is mounted to, that got replaced a number of years ago, and the old version of that mount, which was a similar type but an older one, got transferred out to Kumiu, and we've been operating that with the telescope out there for a while. However, not long after we installed it, probably less than 6 months after we installed it, there was a fault with that mount. It stopped pointing accurately. It started going to all strange places in the sky. That's an image of me trying to troubleshoot the problem, and it turned out that the boards, which at that point were the computer control boards that were about probably 12 to 15 years old, had just developed a fault. There was a fault with one of the RAM chips on there. So as part of that, we contacted the manufacturer, who's also the manufacturer of the new mount, the ME2, and what we were able to do is get a control kit which allowed us to upgrade that mount to the latest electronics, exactly the same as what we were using in the research scope. So we were the first users of this mount in the world, I think, to do this upgrade on this particular vintage of mount, to the point where Software-Bisque, who manufacture it, created us custom cables and custom mounting plates to do the job. So we fitted that and upgraded it so that it was using the same software, and basically it became good as new, and we were able to use that now with the telescope that we have out at Kumiu, which is actually the same aperture as the one at Stardome, slightly different design, to do similar sorts of work, but from a different area in Auckland, which has the advantage not only of slightly less light pollution, because surprisingly for the research work we do, the light pollution doesn't make too much difference, but also because we get different weather. So sometimes we can be observing the same target, and Kumiu may have good weather and Stardome may have poor weather, or vice versa. The mandatory pretty pictures of galaxies, of course, taken from the Kumiu scope. That one's Sombrero Galaxy. That one I think is Southern Pinwheel, but I could be wrong on that one. And we've done some in color as well, to give you a sense of what you can capture with that sort of telescope. The final one you might recognize, the central portion of this is a very been taken by Hubble as a very famous image called Pillars of Creation. Hand back over to Grant here.
Yeah. So basically, we got to the point where we decided that it was a time to use some of the Edith Winstone Blackwell funding to upgrade the Zeiss telescope. So we put a concept plan to the Stardome board. They were very excited by that and gave us approval to proceed. We we'd already decided really to buy the BISC Large Telescope upgrade kit. So this is a kit that BISC produced for large telescopes, and by large they mean Zeiss size and bigger. Zeiss is a 0.5 meter diameter telescope. This upgrade kit can be used up to 2 meter size telescopes, which are enormously bigger than the Zeiss. So we knew that they'd work well on the Zeiss. They cost, I forget, about $15,000 or so to buy. 10,000, okay, that's cheaper. But they came with basically a kit, and so the challenge for the design team and the engineering was how to retrospectively fit these motors to the Zeiss telescope to give us the full robotic control we're looking for. The other thing that was missing from the Zeiss is Zeiss only had a worm gear on the axis that pushed the telescope around and followed the stars, east-west motion. The north-south motion, it was purely unclamp it, push the telescope to where you wanted it, clamp it, and that was it. There was no mechanical drive at all. So we knew that in order to install the BISC system, we needed to have a worm gear fitted to the declination axis. We couldn't see inside the declination axis. It was never taken apart when we redid the Zeiss, restored it in the mid or late, or around about 1998, 99. And so we didn't know how big a worm gear we could fit in, but we wanted to fit the biggest possible. So we just took a punt. It looked like they came as, I think, 12-inch diameter, 15-inch and 18, this particular manufacturer, who made top-grade gears. We figured that we definitely 18-inch wouldn't work. We figured that let's take a punt and buy the 15-inch one, and fortunately I can say that it did fit, and Tony will talk more about that a little later. So those were the two key things to get, and once we had those, the worm gear and worm gear present and also the BISC system, we were able to then start getting going on the telescope. So, yeah, so I go.
Yes, okay. Well, I can take over from there, Grant, if you like. First of all, we had quite a big discussion amongst all of us of just how we would go about this this installation work. And so first of all, we produced a number of sketches of possible ideas, and I think Steve's got a few there we might be able to put up on the screen. First of all, that's the telescope before we started, and you can see the original. One of the things we decided we must keep is these setting circles, which are really an iconic part of the Zeiss, and everybody's got used to them. So we had to, they were one part that was, that part had to stay. So we had to work around that. As Grant said, the declination axis had never been pulled to bits before. So we thought, well, what's in behind there? Should we ask Zeiss? So we wrote to Zeiss, and they said, yes, we may have some drawings, we're not sure. Come and have a look for yourselves if you want to. It'll cost you €25 for each drawing we get out for you. So none of us were planning a trip to Jena, so we thought, oh, how hard can this be? We'll just go for it. So that's what we ended up doing. I must admit, at one stage when we pulled the declination axis out and a shower of ball bearings and little gears hit the floor, I thought, oh my God, what have we done here? We've certainly gone past a point of no return, but we picked all those up from the floor and reused them later, and we'll show you what we did with them when we get round to that part of the talk. The biggest part was fitting this gear that we all thought would go in, but nobody was quite sure. So until we had the declination axis pulled to bits, we didn't know. We were lucky, we fluked it, and just the minimum machining, we got it to fit quite nicely. So here's a little picture of the new motor drive system. You can see it's a two-belt drive, so minimum backlash in the thing, and the worm wheel, of course, which is, or the worm and the wheel, which is the precision parts of the whole thing. So we opened up the guards off the right ascension axis, and you can see in there the worm wheel Grant was talking about before, and this box here houses the worm that drives it. It's a 360 to 1 reduction, and first of all, just in here we had in the old one a secondary worm which I think was 20 to 1 that drove that. So you can see this massive reduction back to the motor. So we still had to preserve this massive reduction in the new system, and we did that via belts. Well, first of all, that's the old system again, and the Zeiss had a method for fixing the worm so it wouldn't move backwards and forwards. They had a little peg device in the end there, which we replaced. We were going to use it first, but then we got into problems, so we scrapped that and came up with our own idea, which we'll come to shortly. But one important part of the telescope, you can see here, is this worm wheel and the brake clamp. Once you unclamped it, could rotate independently of the axle. And this is quite a brilliant idea, and we decided we'd have to keep this idea for the deck drive as well. What it does is if you can imagine when the telescope is working over the sky, it's a 180 degrees sort of segment that it works through, and that part of the worm gets worn all the time. Not terribly good idea. You want to be able to rotate the worm round from time to time, so you're wearing it evenly right over the worm wheel right over its circumference. So that's one of the Zeiss features we were greatly taken with, and we decided we had to keep it. Here's my Michelangelo drawing of the first sketch we came up with for the worm wheel. We were going to use the original Zeiss peg system for taking the end thrust out of it, but we ditched that in the end and went to a whole new worm box and taper roller bearings at each end with an adjustable nut, so you could, just like a front axle on a car, where you can take up the slack in the bearings. So that's that was the original worm box, which we had a bit of an accident with when we were machining it. So, and we didn't like it that much, so we decided we'd scrap it entirely and make a completely new one. When we were talking about the RA drive, there was two options. We could either have this drive here, which was all under the shroud, or mainly under the shroud, but poked out the side. Unfortunately, the big disadvantage of that was that the pointers could no longer be used, and we decided we wanted to keep them. So that drive method was option one, but we quickly went away from that and decided on option two. I don't think this is the final one, but this is one of the SolidWorks drawings we drew up, where we took the belt drive. That's the final one. We took the belt drive through the big flange and put it on the outside where it's all accessible. But the only problem was that flange is 10 mil thick solid cast iron, and we couldn't really get that part of the telescope stripped down, so we had to cut this hole in situ in Stardome, and that was a bit of a mission. I think we've got a few photos showing that. Oh, that's another drawing of the new system showing belt reduction. The total reduction, I think, for that side is 12 to 1 to the worm, and then there's 360 to 1 on the worm. So you've got a total reduction of 4,320 to 1, massive reduction. At when the telescope is tracking, the little motor will only be doing 3 RPM, but it's a stepper type motor, so it's quite capable of doing that. But then when you want to slew the telescope to another object, you have to speed that whole system up, and the motor runs at 2,000 to 3,000 RPM, so a lot faster. The motors are capable of going to 6,000 RPM, but we didn't want to run way up there because that'll just wear out the belt system too quickly. The belt system is a tooth drive belt, all stuff really available locally on the market here in New Zealand. In fact, we bought most of our wheels here in New Zealand because the ones Bisc sent us weren't quite the right ratio, and they didn't quite fit where we wanted them to fit. So we bought these locally, and all that part's all local, so that's good. So yes, that's Mars on a really good night through the telescope. And
yeah, the reason for this is we did all the work up to this point, pulling the telescope apart, getting in a little bit of trouble from Stardome management for taking the telescope out of action without asking, and we got all these drawings made. We got the initial engineering done to get the worm block in place, and then the whole thing had to come to a halt because Mars was at opposition, which means it's at its closest position to Earth, and of course the telescope was needed for viewing. That didn't really happen because just at that time where Mars was at opposition, there were huge dust storms, so the surface of Mars didn't look too exciting to be viewed through the telescope. So we had to put off the disassembly of the telescope until Mars was safely on its way further away from Earth again.
Yes, so here we are starting on the dismantle. We've got a custom-made cradle which we can lower the mirror off the back of the telescope hydraulically. It's quite a considerable weight, hundreds of kilos of glass and metal there, so you can't sort of just undo the bolts and drop it down by hand. You have to lift it down with a hydraulic lift, and this is the first stage of stripping the telescope, getting the mirror out of it, and of course it's an optically perfect piece of Pyrex, so we have to be extremely careful with it. And it's still in mint condition, and of course we weren't going to be the ones that did any damage to it if we could help it. So yes, as Grant said, the telescope used to have a tracking telescope on the side, but in more recent times we fitted a solar telescope, and the sun's so bright you don't need a big mirror or anything, so a small telescope will really pick up the sun very nicely, and it has a hydrogen alpha filter in it to cut down the light, and you can see prominences and see the sun's surface very nicely with that little telescope. Of course, we have to have the main mirror blank completely off when that's happening, because if you magnified the sun through that, you'd do some serious damage. So yes, that's just a little aside there, and this is, well, Steve can probably talk to this. This is more of the electrical side on
That's right.
old,
So as it was delivered from Germany, there was a lot of electrics and I'll not say electronics that were used for the various lights, mainly that were lighting up the reticules on the finder scope and on the guide scope, and lighting for the setting circles that we saw before. A lot of that, and there was also power provided for those instruments that we saw, such as the photoelectric photometer, and that was all provided through a set of very old-fashioned looking now connection blocks. This is inside the telescope optical tube. So we had to remove all of that and disconnect all of that old wiring before we could take the actual telescope off. So you can see this is where the telescope actually mounts to the mount. All of that went all the way through the RA arm, the declination arm of the telescope, and came to a set of good sturdy German connection blocks inside there, and I'll talk a little bit more about that. So once we got all of that wiring disconnected and we got the mirrors out, this is basically where we were left, ready for some further disassembly.
I wasn't quite ready for that day. The telescope mirror was out, and we tipped it over because we knew that it was bottom top heavy at that stage, and it came down like a mighty pendulum. We just got out of the way in time. So we learnt to be very careful with it after that, because there's considerable weight involved in this thing. That counterweight is some 500 kg out the side, and you can see just before we took the tube off, we had to prop that up to take the weight so we could take the tube off. So yes, and the day came when we finally lifted the tube off and the axes off and things, and we had to have a crane outside in the car yard, and the hook came in through the dome, and here's the tube coming off, a little video of the tube being taken off. Grant masterminding the operation there, but really it was our lady crane driver, I think, who was doing the work there. So this is the tube just about off and about to be stored. Now the tube's off, and we're getting to the next stage, which is to take the counterweight off. So the crane's coming back for another lift of the counterweight. We didn't realise it had little mounting points in it where we could have put eyelets in there, but instead we gripped it rather unsafely with the sling and just hoped it didn't slip out of it while we were taking it off. Fortunately, we got it down to the ground without accident.
The crane drivers assured us that it was safe, so rather than saying that we did it in an unsafe way. So the crane drivers were very confident in that sling, but it turns out we didn't need it anyway.
No.
That's actually going back on to show you that there actually are eyelets there that we could have used.
So now we've got the telescope off and you can see the axis exposed, and the next step was to take the this big boss around the outside off and all the wiring out, so then we could see what was really inside and whether we could fit the worm wheel in there. We didn't really want to change this. If we pushed the telescope further outboard, we'd upset the balance of the thing and be some major engineering to put spacers in. So we really wanted the telescope to go back in relation to the declination axis exactly the same as when it came off. So that was part of the design brief.
So all of this wiring, you can see the thickness of the cable that ran all the way through the telescope and it came up from the floor. That was one of the things that we needed to understand, how that was wired, because we didn't obviously want to replace all of these old thick core cables. Our modern needs were more for network cables and USB cables and power cables for the accessories that we needed. So getting that and removing that was one of our challenges. That cable actually went all the way through the declination axis, came out of the other end, and this is where the counterweight was situated, where we saw it unbolting from the crane. And that cable actually did a double back and then went all the way back again. So the cable went in here, it went all the way through. There's that little U-turn, and it came back and then went into this connection block here, from where it went down the shaft here. Arranged in such a way that it had its range of motion without putting undue stress on the cores of the cable. And since this was over 50 years old, that design clearly worked, because we didn't have any problems with that.
So here's the first attempt at how we would fit the gear wheel in, and this one was going to involve having the drive for this axis mounted on the telescope. But we decided that wasn't really going to be very satisfactory, and it would put a lot more weight further outboard. So we scrapped that idea. That's one of my early sketches, and we came to a different arrangement, which I think was probably the next. Oh no, this is another photo. As we were getting ready to strip the declination axis and find out what was in behind the boss that you can see there, that the clamping arrangement is attached to. So
we had to get that axle out so there was the boss, and it was attached to an axle which came all the way through, that we saw the cable coming in. So this was the process we used to push that out.
We had to push it out through the bearings. We thought that might be quite a job because they were big bearings, but Zeiss had done some precision engineering and it came out reasonably readily. And it was at this stage when we drew this part of the telescope out, this shower of, we had our oops moment, and the shower of ball bearings and little gears hit the floor, and that really left us wondering what we were doing, but fortunately we were able to pick up the bits, and we'll come back to that shortly. Here's the team just chortling after that accident had happened.
It's worthwhile mentioning the three people in there. Obviously Tony's on the right there, but this is Andreas, and he was our SolidWorks guru. He's the one that did all of the drawings, so we now have a full 3D rendering of the work that we've done, so that could potentially be useful to somebody else who's going to upgrade one of the other 30 or so of these telescopes there are in the world. And then our engineering guru from Pakuranga Engineering is Raj, and these two people were key members of the team in our ability to get this done.
Raj is an amazing guy. He goes for absolute precision, and which is exactly what we wanted. So the engineering work has been to a really high standard, and I think Zeiss would be proud that we've maintained their traditions there. Yes, that was just after the oops moment, I think. We were looking at where we were going to fit the worm wheel in there and realising we'd have to do quite a bit of machining. So we'd have to take this axis away and take it to Pakuranga Engineering, fit it up in their big lathe and get it done. Well, that was the bit that caused all the consternation. But fortunately, we don't didn't reuse this planetary gear. It was all part of the old slow motion system, no longer needed because now you just push a button and the electrics will take it to wherever you want to go.
The bit of an aha moment that the team had once this was disassembled was looking at the inside of this brake. So this is the brake system that Tony talked about earlier, which essentially clamps the telescope in position when it was being used manually. And on the inside diameter of that, when we looked at that, we thought, that'd be interesting to measure that, because that kind of looks not far off the gear we bought. So out came the tape measures to work out that it actually would just fit. It might need a little bit of truing up, and as Tony just mentioned, by getting that into the machine shop. But it allowed us for a whole new plan where we would take this worm gear that we bought, we'd mount it inside that boss. We would have to cut a section of that off to put the worm in, but we'd end up with something that looked a lot neater. We just have to come up with something that we could use for that brake in order to replace that or do something else on there. But in terms of serendipity, that was probably one of the high points in the disassembly. Yes, to realize that the gear that we bought, and you may have seen Grant's image of the worm gear earlier with the crossed fingers. It was like, yes, it was a great decision that had been made about 2 years earlier from where we were at this point.
Yes. So here's the, I think we've just loaded that part into the ute, ready to take it out to the machine shop. And this is just prior to that, where it's being ready to lift it off the right ascension axis, the declination axis. Here it is, going out through the dome. Quite a big chunk of metal, probably 400 or 500 kgs in weight. So you have to be reasonably careful with it. Manoeuvring it into the ute, ready to take it away to Pakuranga Engineering. And here's the final arrangement we came up with. I was talking to you about before. You can see we had to shrink ends onto the existing worm where we decided to keep it. The earlier worm that went on the front of it was badly worn, but when we did a projection microscope check of this worm, we found it was in very good condition. Probably because it only does a quarter of a turn per minute when it's driving the telescope, so the chances of wear are pretty slight, even over a period of 60 years. So we decided we'd keep the worm. We didn't really want to make a new one because it was really a precision bit of equipment. And you can see the two roller bearings, they're new. We fitted either end, and you can see the preload nut where we can take all the end float right out of the worm, which is pretty critical. We want to get, when the telescope's there's the final arrangement after it was all built and in the new worm, fitted in the new worm box. So yes, you want to get this backlash. You can't really have much backlash there at all between the worm wheel and this, so the mesh has to be very tight. And we fortunately got it back together very good, easily, and we didn't have to put make much adjustment at all to get it back to where it was and take all the backlash out of the thing. The idea being, when it's tracking on an object, magnified object in the sky, you don't want any more than 2 or 3 arc seconds of movement in the wrong direction there, because over a long exposure photograph, could be from seconds to minutes, the stars will look all blurry if you're going to have backlash there. So very critical piece of equipment, this worm and wheel. That's the RA axis just before we started seriously working on it. And here we are, as I said before, we decided on having the drive for that axis out the back rather than under the covers, which was going to interfere with the pointers and things, and we'd have to remove them, and we decided we weren't going to do that. So a bit of precision engineering going on here. Raj is cutting through the 10mm plate and then drilling it all out. So yeah, high precision engineering, but we weren't too happy about that. But we did get there in the end, and it all worked very nicely. Completely opposite to the hole we had to make in the other flange, which we'll show you shortly. There's Andreas putting the final touch with a file to it. So we're very pleased when that was all done. We had to protect the worm, of course. We didn't want any of those filings getting anywhere near it. They made a lovely grinding paste, which was absolutely forbidden. So yes, there's the holes cut in it, and we're ready to start mounting the new drive to the RA at this point. So there's Raj fitting up the belt drives he's installed the new RA drive, and he's fitting up the belts to it there. So that was the first part of putting the telescope back together again. That's another shot of the new worm box and the worm wheel to the side there, and there's the final drive. And you can see it's a very neat, tidy drive compared to what used to be on the telescope, and much more versatile because we can use it for slewing as well as driving now. So yes, that's the first stage of putting things back together again, getting the RA side set up. So this is just a general view of Pakuranga Engineering, where the telescope was taken to. On the left there, you can. Oh,
sorry.
That's all right. No, don't worry about that. Keep going again, Steve. On the left there, there's the biggest lathe which was needed to put this in and get onto it. And Raj is getting ready to do little. There wasn't much machining required, just a little bit of machining to get the worm wheel to fit. There he is doing the precision part. That's another shot of the same thing. You can see the cut metal there, where we had to just take it down a level and cut that metal away to get the worm wheel in. We kept the Zeiss had a hardened piece in the middle there. You can see it was screwed in there, which we kept for running the worm wheel against. We were thinking of having a bearing there, but then we thought, well, no, the bearing's a beautiful bit of bronze. We'll have just a nice plain bearing there and a really good precision fit over that sleeve, and that's what we ended up doing. So it worked extremely well. That's the one. You can see how we've mounted the whole arrangement into the existing there. The dark grey is the new boss we had to make. We'll come to that in a minute, and that replaced the old Zeiss boss. The brake is now on the outside nearer the telescope rather than on the inside. And on the inside where the brake went, we now have the worm wheel and the drive system coming through the big flange there and driving it. So you can see that one's the worm wheel there is a 450:1 ratio, and so the belt drive is a wee bit less than what we had on the RA axis, but we ended up with the reductions both on the RA and the deck axis exactly the same, 4,320:1. And it's not necessary to have that, but it just made things easy if we kept them both the same. You can see the originals. Oh,
sorry.
No, you can see the original Zeiss bearings in there, which we retained, and other bits and pieces. Then there's the new thrust bearing under the bronze bearing. You can see just the little balls right on the bottom there. Those are the balls rescued and made into a new bearing, which we'll come to in a minute. So here's the deck axis on the mill, the biggest mill, the CNC mill that Pakuranga had, just prior to cutting out the hole. You can see it's a much more precision operation to our on-site one for the other axis. So that was all. Once that was all done, we could start assembling the declination axis, and it's back on the bench. We're just painting up the cut edges and getting ready to put the declination axis back together. Then here's the bearing. We had to make a new thrust bearing, and those are the rescued balls and spaces we got off the floor from under the table and down cracks in the floorboard and wherever they fell. Probably a few left, but we got most of them. And here's the worm wheel fitted in onto the new hub, and assemblies starting to go. Have we got any shots of the hub before we go too much further, Steve?
Of which side, sorry?
The ones at the foundry and...
oh yeah, we've got that just coming up. Funny you should say that, because it's the next slide.
Oh, okay. That's the hub after we finished machining it. We did our machine drawings. You could see to make that thing from a solid billet was going to be a bit of a silly idea. It's 436 mils in diameter, And if you'd imagine a big lump of steel or cast iron that size, it's a colossal amount of machining work. So we decided we'd get this cast, and not just cast in any old thing. We decided we'd get it cast in SG iron, and of course A&G Price down in Thames are the experts in casting SG iron. So we commissioned them to do that, and that's the day our boss was being poured. We travelled down there to see it going, and it's an old foundry, but by gee, these guys know their work backwards, and they make beautiful castings. It's great to see they're still going, and they didn't get closed down when they went into liquidation a year ago. Here's the boss after it's been machined. You can see it's just a perfect bit of SG cast iron. It's come up perfectly. We used SG cast iron because it's a very stable material. We don't have to stick it out in the backyard for a year to weather to get all the stresses out of it. SG iron you can just work on straight away, and that's what we wanted to do. We didn't want to muck about. So it all came out beautifully, and there it is mounted back onto the telescope, and the worm wheel is underneath it, and we're starting to put everything back together again. Here's a general, these are the sort of SolidWorks drawings we did, that Andreas did. You can see the assembly there. We had to make a new arm there in the right-hand photograph. You can see that grey coloured arm. That was a new arm because we'd moved the brake further out on the telescope, and we wanted to marry up with the other torque arm on the telescope. Zeiss had a few very nice features in their telescope we decided to keep. You can see on the left-hand drawing there's a housing halfway down just past the opening there, and that device is a stop, so you can't turn the telescope upside down. And there's another stop in the RA axis. We knew it was there, but we never really understood how it worked. But while we had the telescope all to bits this time, we figured it all out, and we kept all those Zeiss features, which are pretty important. I think they're part of the Zeiss. They're brilliant bits of engineering, and so they're all back in there again. And here's the drive in the final stages. You can see we had to make some aluminium mountings to take various parts of it. And we had to do quite a bit of 3D printing for all the guards to go over the different covers and things. And Andreas did all those on his 3D printer. We drew them up and then just printed them. There's the printer making that one you just saw a minute ago. Made quite a lot of those guards, and the telescope was all nicely guarded up. Then finally the day came when we brought it back to Stardome. And here it is right on the back of Raj's truck, and ready for the crane to lift it back into the dome, and there's the lift underway. And inside the dome, and about to marry back up to the right ascension axis again. It's a wee bit difficult to do because you're not lowering it straight down onto something, you're lowering it onto a face that's at 37 degrees, as Grant said, and took a bit of juggling just to get it back in again. We made some special tapered pins to help ease it on, so we got it on fairly easily and quickly.
With the telescope reassembled, at least partially, it was back to me to start coordinating getting the cabling through, because when we fully assembled it, we wouldn't, for example, be able to have access to this turning point for the cable, which is covered up by the counterweight shaft. So working with another team member, Tony Burns, we'd built a customized cable loom that had all of the cables we think we'll ever need for the telescope. It includes network cables, USB, power, some small signal cables and lighting cables, and get that to a bundle where it was about the same size as the original bundle and following the same cable path, so that we would not have any stresses on the cables in the same way that the 50-year-old Zeiss cables had survived. The other job, and you can see in this view here that there's a ribbon cable there. This is from the control system, from the Zeiss control system. One of the features of the Zeiss Telescope control systems is it's got a hardware index point, so that the telescope can return to a home position to a really accurate degree. And the way they do that, using fairly non-precise components actually, is to use an opto-slotted switch riding across a physical edge, so the telescope tracks so that edge the metal edge interrupts the light beam, and then it cycles in and out until it finds the point which is right on the edge of that, and that actually gives really accurate. Grant, you might know what the accuracy is in arc seconds of that home position.
Yeah, it's probably about a quarter of an arc second.
So we had to fit that onto both axes. Once again, Andreas's 3D printer came in useful for making the mounts for these, and here you can see this is the interrupter plate. So this is well, not quite semicircular. I think it was about 240 degrees. Where once the telescope rides off the edge of that, this opto sensor here detects that. So Andreas's 3D printer came into good use once again to build these brackets to allow these sensors to detect the home position.
We didn't want to have these exposed on the outside of the telescope, so we built them into the axes themselves, or one under the cover and one into the axle. So they're nice, tidy little units. You can't see them when the telescope's all together, but they're definitely there underneath the whole thing. So we wanted as much as possible to keep the Zeiss looking just like it did before we started. And I think when you see the final drawing, you'll appreciate that we got. You can be our judges, but I think we did a pretty good job there.
So it was at this point with all the cabling in, and you can see we've now got the motors plugged in. With the motor cables, we've got the home sensors plugged in. So before we put the telescope back on, we needed to check that these motors drove the axes in the way that we expected them to. So getting the drive systems hooked up, the system hooked up to the computer, all of the sensors attached. We just had one problem though, as the telescope came out of the factory, it was balanced with there being no telescope and no counterweight on there. But since we added this great big piece of ductile iron on the end of it, it was now no longer balanced. So as we were doing some testing, in order not to put stress on the motors, we had to add a little bit of counterweight. In the end, one night working around Stardome, Tim Natush and I were looking for something we could add as a counterweight just to make it so that it was balanced for testing it. That ended up being a bottle of soap and a bottle of chocolate sauce out of the kitchen. So there's actually was a fixture on there as we were testing for a good couple of weeks. I'm maybe not sure that Victoria should see that, but yeah, the Stardome kitchen came into use for that. And then it was once we had that balanced, we could do our first testing to make sure that the mount actually worked. So this is a video of the very, very first time we had the mount driving all by itself under computer control. You can see there's no telescope on the right hand side here, and there's no counterweight other than our chocolate sauce and soap on the left hand side. And you can see the motors moving in there. You can't really see these ones under the 3D printed cover. But this was a really exciting moment because it meant that the drive systems that we'd chosen all worked cleanly. We were able to move the mount through its full range of motion. We could check that all of the worm and gears performed properly. They didn't bind up. The motion was smooth. And it was, this was kind of... astronomers talk about first light for a telescope. Well, first drive for a mount is probably just as important, and it's certainly just as exciting for us. So then it was time for the crane again. There's our eye bolts we missed the first time. And we've got the telescope tube mounted back on there. No mirror yet, which is why we have the prop in place, because the counterweight is heavier than the telescope without the mirror. We had the telescope tube also supported at the end there at this point. Because if you remember at the start, we had to pull all of the wiring out of the optical tube. Now before we put the mirror in, we had to put all that wiring back in with the new all the new USB and network cables that we're running through. And finally it was time to get that mirror and put it back in place. I guess the next most important part, which was to test the telescope out will it drive with the whole weight of the telescope and counterweight. You'll see that there's a door covering the telescope tube here, and there's actually only one fitted at this point. Grant's probably going to hide behind his chair now. We had a bit of a sad incident at the time we were doing the work. Grant took one of the doors to the paint shop to get paint matched, and unfortunately that day his car got stolen with that piece of the Zeiss Telescope in the car. We never recovered that piece, but as luck would have it, we actually decided that was fortune, and we made some new lightweight doors that I'll show you in a slightly later slide. But at this point, the main thing was to get it running. So here's a small video of the telescope in operation once we had everything mounted.
Yes, the dome will have to come around further.
So you can see the motion's very smooth. The motors start and stop with the accelerate and decelerate. That's all through the drive control. And as Grant was saying before, the accuracy of it pointing to the area in the sky where you need it to point is just incredible. If you imagine the size of a planet, you imagine the size of Jupiter, the pointing accuracy is many times smaller than the size of Jupiter when you're looking through the eyepiece. I think we talked about the other day, it was about the 10th of the size of Jupiter or something?
Yeah, the RMS pointing model should give us about 8 or 9 arc seconds, and Jupiter's about 40 arc seconds, so it's very precise.
And these were the new doors that we built to cover the telescope. Again, with some more of Andreas's 3D printing, unpainted at this point. I think it might still be unpainted. We built a drive system that's not attached just yet, which will allow us to open and close the telescope for remote operation. With the telescope in place and ready to go, the next job was looking at our old dome. So the dome that Grant talked about that was supplied with the telescope 50 years earlier was motorized. So there was a hand controller that I've actually got here. I can probably show you. This is the original Zeiss hand controller, and that controlled the rotation of the dome, as well as originally some change for the secondary mirror to allow that to change position. What we wanted to do is to be able to slave the dome rotation to the movement of the telescope. The old 3-phase motor, which you can see in this image here, was just fine, but the level of control that we had to manage that was really just a clunk on and off, and actually that was wearing the rack system around the edge of the dome quite heavily over the years. So we installed a new 3-phase motor controller, which we were able to then get computer control of that and attach that into the system. You see Tony Burns, who was the volunteer who helped with all the wiring here, as we're putting together the I think that was the serial cable for connecting into the computer. So now the rotation of the dome is now perfectly synchronized to the telescope. So as the telescope slews to a point in the sky that you need to observe, the dome slews around with it, and the slit in the dome is perfectly aligned with the telescope. And that was really the main part of the of putting it back together, other than putting the covers on there. Some of Andreas's 3D printing in the covers. We tidied up the wiring, put some nice neat boxes on there, and yeah, it was really ready to go. The only final part was the fact that we'd taken the mirrors out. Now, when you disturb the mirrors in an optical system and you put them back in, you've got to get them aligned. So Grant talked before that the Cassegrain system has got 2 mirrors. It's got a curved primary mirror and a curved secondary mirror, and those 2 mirrors have to be aligned just right so that when the light comes in, it hits exactly the center of the secondary mirror, and that gets reflected directly down the center of the optical tube. So that's a process known in astronomy as collimation, or it's known in optics as collimation. So we used a specialized telescope that looks down the center of the telescope axis, and a camera on the end of there to do the collimation, and here's the view that the camera saw. and you use this to align these two axes. So I'll not go into that. There's probably a whole video all by itself of how to collimate. That's the new doors fitted, and you see they're still purple, and you can see the highly I won't say polished, they're coated with aluminium mirror of the primary surface of the mirror. That's showing the doors closed, and these are just some general. This is the control box. That was the purpose of this slide actually. The control box here, which shows where all the electronics that we fitted go. And then just a couple of general shots of where the motors are. This is, you can see we've been very sympathetic. The pointers that are not required anymore, these pointers that point at the setting circle here with the light on there, used to be critical because you would manually point to the appropriate number as determined by the software program on the computer, and now it just points. But in order to keep that look, we put the pointers back, put the lights back, and that's really what you see today. There is only one more piece of the puzzle that we had to do in terms of engineering, and that was in order to operate the telescope fully remotely, and Grant operates the research dome completely remotely, we needed to have a way to open and close the shutters on the telescope, which is why we built the doors with the motors on. We can already operate the telescope remotely. We can already have the dome rotation synchronized with it, but we've also got the shutter in the dome, the doors which open, and we needed some way to automate those so that we could open and close those from computer control as well. So this was back to some of Tony and Andreas's genius in looking at the old hand wheel control that we had to open up the doors. And over to Tony again.
Yes, and originally there's just the hand wheel went through to those chain wheels on the side, so we had to incorporate a 12-volt worm box to motorize it. So we rebuilt the bracket, and now there's a little clutch in there. When you pull the hand wheel out, it disengages the motor, and you can turn the chain by hand, or if you push the wheel in, it engages the motor, and the motor will do the job for you. We haven't actually got that system wired up yet, but that's the next stage of the project. It'll be a 12-volt system, and it'll be powered by a battery on the dome, and that battery will be charged by a solar panel on the outside of the dome. Just another shot. We just gave it a trial to see how it would work. You can see it pulling the dome together again there. Yes, so that's it from the mechanical side, and thank you very much.
So we got a couple of leftover questions. We do have some time for questions, so if you do have any, get them in the chat quickly, and we'll get through as many as we can. We did talk through a couple of those during the course of the talk, but another question, which is from Samira, and I'll probably give this one to Grant, is would Elon's Starlink satellite constellation really affect observatories like these?
We think not. At the moment, there could be up to 12,000 of those satellites up there, but when the sky's got a lot of area. I mean, as it is now, we have satellites go through our field of view and leave a streak on our images. It doesn't affect the science much for us, the type of science we do. And also our telescope's not enormous, but the problem's a bigger one for very large telescopes, maybe 6 metre, 8 metre type class telescopes, which are enormous, and with big fields of view. So in which case it'll become likely in the future that they'll reach a time where they won't be able to take an image without having streaks on it caused by satellites. That doesn't affect us, but it will affect the big multi-million dollar and billion-dollar telescopes.
And another question here from Keith, who wants to know if the Zeiss company still exists.
Yes, the Zeiss company is alive and very well, still making high-precision telescopes. Some of their telescopes, I think the biggest Zeiss one I've seen is about 2.5 meters or 3 meters, but they make telescopes much bigger than our one, and they make them right down to quite small amateur, more amateur class backyard telescopes as well. They're one of the world's famous optical companies, and still located in Jena in Germany.
There's no more questions on there. I'll just give it another minute or so for anybody else if there's any final questions. But for me personally, I just want to say thanks to these two guys, plus our other helpers and volunteers, and also Stardome for the opportunity to be part of such a really important project to bring something which is iconic to many people in Auckland who've grown up with this observatory. And yeah, I think it was just a fantastic experience. One more question just before we go. I've got two more questions actually, which is great. John wants to know, is the mirror overcoated? And if not, how is the mirror's aluminium coating? I can answer that one for you. The mirror isn't overcoated. We are expecting it to be the next time we re-illuminize it. It survived its experience of being out and stored pretty well. We did do some really light cleaning to it for a bit of dust before we put it back in, but it is ready for another illuminizing. And I think COVID's put a little bit of a dampener on our ability to get this done this year, but certainly it's usable in the interim. But there will be another illuminizing very soon, we're hoping within the next year. Jason wants to know if we had to retract the mount after the earthquake the other day.
Well, we don't think so. The mounting, the grey mechanical part you can see there, and its pedestal sits on a large concrete plinth that's under the floor, and it goes down it's about 1.5 meters square at the top, and it goes down about 6.5 meters to be anchored onto a basalt flow underneath. So the amazing thing is that this mount, when it was first installed, was aligned by a guy I knew quite well. He was one of the sort of legends of the Astronomical Society, Trevor Rounthwaite. He was known for being extremely fussy about getting things right, and he got the job of aligning the mount to the Earth's rotational axis. And it's perfect. It's as near perfect as you could get. I wouldn't dare touch it. And I don't think the earthquake will have had enough power to shift this mount either. So hopefully not.
Another question for Grant here, which, because I know he'll enjoy answering this one. This is from Miles, and it's, can you see a time when full digital can replace analog vision in telescopes?
Well, I mean, basically what I do is only do digital with the research telescope, so the answer is yes. I mean, their CCD cameras are digital, and so most all imaging systems are digital. So the only time it's used analog in an analog sense is when you put your eye to it today. You know, any camera system we put there now is digital in its nature. It's just our eyes that aren't. So it still going to have a long life ahead of it as a look-through telescope for the public. They get a great buzz out of looking through it and seeing the moon and the planets and star clusters and other things. And you can't kind of beat that experience totally. But the new life it'll have now is the ability to do some serious imaging with. We've got a very good CCD camera for it already. I haven't really used it in earnest yet, which we're looking forward to doing. But that's all totally digital.
And just a couple of final ones to finish off. John wants to know, what are some of the planned projects for the scope? Well,
they'll probably be dovetailed in with what we do with the other the research telescope, which is full-time research. There's lots of projects where we want to watch the light changes of a star. It could be a binary star, it could be a pulsating star, or even more exotic objects like quasars and things like that, which can be imaged. Each telescope could be looking at the same target with different filters, so we could do simultaneous measurements in 2 different filters from the site, and that would be quite an interesting bunch of opportunities that we haven't had before. You know, with all robotic telescopes like this, remote controlled ones, you can just, there's just a huge number of targets to do. The sort of work we do with other people. We don't initiate that much stuff that we only do from Auckland. We're working with people that are using telescopes simultaneously in Chile, Australia, South Africa, other ones in New Zealand, monitoring things like events that take place over a number of days. And by having multiple telescopes spaced around the world, you can keep these objects under observation during darkness for extended periods of time. And that's what's leading to great advances in the understanding of these objects. The one telescope operating at 1 longitude can't do. So, I mean, this telescope will be used as part of that sort of network of observatories.
And the final question, which is just a quick one, it's from Keith, and he says he presumes the counterweight had to be repositioned for the adjusted weight. And it did, but it was surprisingly little. Can you guys remember how much we had to move that? It wasn't very much at all. I was quite shocked. Well, I guess it was the weight of a bottle of chocolate sauce and a bottle of soap. So, not very far.
Yeah, no.
So, thanks, Grant and Tony. Thanks for Stardome.
Thank you.
Pleasure.
And thank you, everybody who's watched. And I hope you have a good evening.
Thanks, Steve.
Thanks.